So suppose you have a question. There is a rod of mass m and length L which is free to move on a table, and a particle of mass 2m comes and hits the upper end of the rod at an angle of 90 degrees with the rod. Coefficient of restitution between 2m and the rod is given to be half. And a particle of mass m with velocity 3v comes and hits the lower end of the rod at an angle of 90 degrees, and the coefficient of restitution is given to be, say, 0. So that means it comes and sticks with the rod. So find final velocities. So first step should be what? Draw the velocity diagram just before collision. So this is our step 1, which is already done. We know the velocity diagram just before collision. So next step should be what? We should draw impulses acting on each body during the collision. So we can say this particle, an impulse of, say, I1 acts on this particle when it hits the rod. This is basically your normal reaction, which has become impulsive in nature. So it acts for a very small time, and suppose therefore an impulse of I1 is gonna act on the rod towards right, and the upper particle experiences an impulse of, say, I2. So this rod is also going to experience an impulse of I2 in the opposite direction. So this is our step 2, part 1. This is our impulse diagram. Step 2, part 2. This is our impulse diagram of, this was impulse diagram of each body. Step 2, part 2 would be impulse diagram of system. So if we consider this rod and these two particles to be a system, then there is no net impulse on the system. So step 3 would be our velocity diagram just after collision. So we can assume, let us assume velocity of center of mass of rod just after collision is, say, VCM, and it also starts rotating, suppose, in anti-clockwise direction with some angular velocity omega. So it's just an assumption. Your directions might be opposite to what I have assumed in final step. So they will just, values will just come out to be negative. So don't worry about it. Then we can say, suppose this velocity of this particle just after collision is, say, v1, and velocity of this particle just after collision is, say, v2. Although I already know these two are going to stick just after collision, but let's assume this velocity is v1 and let's assume this velocity is v2. So I have basically 4 unknowns. Look at the velocity diagram. They are basically your v1, v2, vcm and omega, and I need 4 equations. 2 equations can be formed using coefficient of restitution. So at the topmost point, V separation should be equal to EV approach. V separation equal to EV approach should be applied along common normal. So in this particular case, this is our common normal. In final state, this is our common normal. So V separation equal to EV approach along this particular common normal at the topmost point. So V separation, I need to find velocity of this particular point. Look at this red mark. I need to find velocity of this particular point just after collision. Its velocity is going to be in this particular direction, L by 2 omega minus VCM. velocity of this particular point just after collision in this direction would be L by 2 omega minus VCM. So V separation at the topmost point would be L by 2 omega minus VCM plus V2. This is our velocity of separation at this particular contact surface is equal to E. E is given to be half into velocity of approach. I need to find velocity of approach of this point and this point along common normal just before collision, along common normal, along this particularly this line just before collision. So it comes out to be V. So this is our equation 1. Doing the same procedure at the lowermost point, another point where collision is taking place. So this is going to be our common normal, and this is going to be our common normal. So velocity of separation, I need to find velocity of this point just after collision. So velocity of this point is going to be VCM plus L by 2 omega. So we can say V separation at this particular point just after collision is going to be V1 plus VCM plus L by 2 omega is equal to E. E is going to be 0 into velocity of approach. Velocity of approach is going to be 3V. That's our equation 2. We are not yet done. We need 2 more equations. We need 2 more equations. Look at this particular diagram. That is your impulse diagram of the system. We can say net impulse on system is 0. So there is no net linear impulse acting on this particular system. Which system? Of the rod and the 2 particles. So I can say linear momentum of this system is going to be conserved. So we can apply conservation of linear momentum. But remember, we can apply conservation of linear momentum of system. I cannot say your linear momentum of this M is conserved. No, it's not conserved. Impulse I1 is acting on this particular M. Of 2M, it's still not conserved. Impulse I2 is acting on this 2M. Of the rod, no, linear momentum of rod is also not conserved because net impulse of I1 minus I2 is acting on the rod. I can apply conservation of linear momentum of system. So we can say, let's assume this direction to be positive. Initial momentum of the system would be momentum of 2m plus linear momentum of m plus linear momentum of capital M. So we can say capital M into 0. This is our linear momentum of capital M just before collision plus linear momentum of mass M. Mass M is gonna be M into 3V. Why 3V? Because this direction I have assumed towards right to be positive and velocity of this M just before collision is towards right plus 2M into minus V because it's in opposite direction. This is our initial linear momentum of the system that should be equal to final linear momentum of the system. That's gonna be M VCM plus 2M V2 plus M minus V1. This is our equation 3. We are still not done. Now again look at this particular system impulse diagram of the system. There is no net linear impulse on the system. We can also say angular impulse on the system about any point is 0. We can say angular impulse on system about any point is 0. That implies I can apply conservation of angular momentum on system. Remember, on system about any point. So if we have the freedom to choose our point, we should choose a very convenient and very nice point or something. So this nice point, which can be this nice point? This can be our nice point A or B, or let for that matter C. Center of the rod. Center of the rod. Look at this step 1 figure on the step 1. I am saying I can choose any point about which I can apply conservation of angular momentum on the system, and I can see three very nice points, A, B or C. So let's choose C. Let's choose C. We have to basically write equation for angular momentum for M, 2M and capital M just before collision, and we have to write equation for angular momentum for M, 2M and capital M just after collision, and we have to basically make those two equations equal. So let's assume, let's choose some positive direction. Let's say this is our positive direction. I'm assuming anti-clockwise to be positive and consequently clockwise to be negative. So what's our angular momentum of this 2M about C just before collision? That's going to be 2M V L by 2 plus M 3V L by 2 plus capital M into 0, it's at rest. So that's our part 1. That should be equal to angular momentum of the system, that means angular momentum of M, 2M and capital M about C just after collision. So that's going to be 2M. Now this mass was M and this was 2M. 2M V2 L by 2. 2M V2 L by 2. Now look at this direction about C. It's going to be clockwise. So we put a negative sign over here. Of particle of mass M would be mv1 L by 2. Now this angular momentum of this mass M about C is again in clockwise direction. We put a negative sign over here. Plus capital M L square by 12, that is ICM omega. Now what's your angular velocity about C? It's actually anti-clockwise. So we put a positive sign over here. Look at this positive sign. So take care of these signs, otherwise you are going to make some mistake. This is our equation 4. 4 unknowns, 4 equations. We are done.